So in this video, I'm going to talk about something that I think is pretty interesting. It's a surface of revolution. You saw this in Calc 2. So we have some curve, r of t, parameterized by x of t, y of t in the xy plane. T goes from a to b, and we're going to revolve this around the x-axis. We could revolve it around the y-axis too, but I'm going to revolve it around the x-axis. Okay, so we revolve this around the x-axis and we get a surface. And now we want to do surface integrals on the surface. So we're going to have to do two things. We need a parameterization for this surface, and then we're also going to have to compute the normal vector or the rt cross r theta vector. The other parameter is going to be theta, and then we also have to, find the magnitude of that vector. The example in the homework is something like r of t is equal to t minus sine t, t minus or 1 minus cosine t. And here t goes between 0 and 2 pi. It's not so important. I think it's good just to do this as a generic example because there's going to be some trig functions, and it's easier to see what's going on with the trig functions if we don't have other stuff going on. So I'm just going to do it in this generic form, and I'm going to try to graph this curve in the xy plane. So the curve I'm going to sketch is inspired by the parameterization from the homework, or the curve from the homework, but I'm just doing that so we have something to look at. You can think about any curve that you want. Okay, so this is the curve in the xy plane. And now I want to try to illustrate this in the xyz 3 space. So this will be the z-axis. Then we have the x and the y-axis. Okay, and now I want to sketch this curve in the xz plane. And this curve, as I sketch it, this lies in the xy plane. Okay, so it doesn't come out of it's not coming out of the xy plane. This lies in the xy plane, and we're going to revolve this curve around the x-axis. So this is kind of what it looks like, and let me try to draw some curved lines to indicate that it's a surface of revolution. I mean, you guys know what a surface of revolution is. You're just going to have to get past my bad drawings. Let me try to get some dashed lines in there to maybe, make it look a little more like a surface of revolution, though I don't think this helps so much. Anyway, the idea is that what we have to do now is come up with a parameterization for this surface. Okay, so given a point on the surface, we want to find what it is in terms of parameters. So we're going to keep one of the parameters. One of the parameters is going to be t, but it's a surface, so we need another parameter. So we'll call that theta. And theta always represents an angle. It represents an angle here. T goes between a and b. Theta is going to go between 0 and 2 pi. And again, you'll see what this theta represents in a moment if you don't already kind of see. And so let's let this green dot here that I just drew on the surface, this is a generic point on the surface. It has coordinates x, y, z. We need to figure out how to write each one of those coordinates in terms of t and theta. And so we'll start with the x coordinate. So the x coordinate, like all the coordinates, are initially a function of t and theta. So we want to figure out what x of t theta is in terms of t and theta. Okay, so let's think about this. So what is the x coordinate going to be? Well, the idea is that it's just that point. If I drop a line down to the x-axis, that's going to be the x coordinate. But that's just x of t, where the x of t is coming from the parameterization. Okay, now y of t theta and z of t theta are a little trickier, but the basic idea is that we're going to write y and z in terms of polar coordinates. So what I want to do now is take this shape and project it onto the yz plane. So the x coordinate tells us how far out on the x-axis we are. Now the y and z are going to tell us where in the yz plane we are. So if I take this shape, say this red curve here, and it's a circle, I'm going to draw this in the YZ plane, and I get something like this. Okay, so I've just taken the shape, taken the region, taken the surface, projected it onto the YZ plane. And the part that I'm looking at now is this red circle here. And I'm going to write this YZ in terms of polar coordinates. Polar coordinates in the YZ plane. So I need to figure out what the radius of this circle is. So now let's go back, excuse me, let's go back to the surface in the XYZ 3 space, and the radius of the circle is just this weird multicolored line that I just drew. Okay, so what is that? Well, that's y of t. So why is that? Well, to convince yourself, let's go back to the xy plane. So this green dot represents the same, or this weird colored dot here represents this weird color dot here. I can't figure out how to get a better color right now. And that distance is y of t. That's pretty clear. But that distance is the same as the corresponding distance that I drew, and that's just the radius of the circle. So the radius of the circle is y of t. So in polar coordinates, y is equal to r times cosine theta. So y is the horizontal axis, z is the vertical axis. So y is r cosine theta, z is r sine theta. Here the radius is y of t. So y is equal to y of t cosine theta, and z is going to be z of t sine theta. So what this means then is that y of t theta is equal to y of t times cosine theta. And z of t theta is equal to z of t sine theta. And again, the idea is we're just taking the red circle from the surface and projecting it onto the YZ plane, and then writing that in terms, and then writing the y and z coordinates, using that to write the y and z coordinates in terms of polar coordinates in the YZ plane, and that gives us y of t cosine theta and y of t sine theta for the y and z coordinates. Okay, so this is the parameterization for the surface. X of t theta is equal to x of t, y of t theta is equal to y of t cosine theta, z of t theta is equal to y of t sine theta. Now let me clear the screen so we can do some computations. Okay, so this is the parameterization that we came up with. And again, x of t and y of t refer to the parameterization for the curve. I'm using r of t to be both the parameterization for the curve and the parameterization for the surface. You'll just have to follow along, but I'm doing the parameterization for the surface in green. So now let me compute rt cross r theta. So remember, this is just the determinant of this matrix. And then the rt vector comes first. This is x prime of t. I'm just taking the derivative with respect to t. Y prime of t cosine theta, and then y prime of t sine theta. And this is where I think it's very helpful to just have x of t and y of t instead of a formula for x of t and y of t, because we're going to be able to see some nice trick stuff happen that is a little more complicated and obscured if you don't have, if you actually have expressions for x of t and y of t. Okay, so now we're going to do the cross product. So if we look at the determinant on the right-hand side, the columns on the right side, notice what we get is y prime of t times y times cosine squared plus y prime of t times y times sine squared. So together, that's just y prime of t times y of t. Okay, now for the next component, it's going to be the determinant formed by the outer two columns. That's going to be x prime of t, y of t, cosine theta, or it's negative, the determinant. So it's going to be minus x prime of t, y of t, cosine theta. And then the last component is the determinant formed by the first two columns, and that's going to be minus x prime of t, y prime of t, sine theta. Okay, so this is the RT cross R theta vector. Now we would need to determine, if we wanted to do the line integral of a vector field, we would need to determine whether or not this is the outward pointing normal vector or the inward pointing normal vector. And the best way to do that is just to pick a point, pick a t and a theta within the parameter domain, and see if that is an outward pointing vector or an inward pointing normal or an inward pointing vector. If it's an outward pointing vector and you want an outward pointing vector, it means that this vector is going to be outward pointing for all t and theta. So you just leave it alone. But if it's inward pointing and you want outward pointing, that means it's inward pointing for all t and theta. So just multiply it by -1. Okay, but I don't want to talk too much about that in this. I mean, I'll leave that to you when you actually try to solve some of these problems. But the other thing that we need to do is if we want to do the surface integral of a scalar field, we need to compute the magnitude of RT cross R theta, and so that's what I'm going to do now. And so we're hoping that some trig identities will save us. So the magnitude of RT cross R theta is going to be the square root of y of t, y prime of t squared, plus, and now let's look at this. In these two terms, it's x prime y cosine theta and x prime y sine theta, or negative those two terms. So when we square them and add them together, we're just going to end up with x prime of t, y of t squared. And what is this equal to? Well, now both of the, actually, wait a second, that's not, that second term should not be y prime of t, it's just y of t, typo there. Okay, so each one of these terms has a y of t squared, so I can factor that out. And so what we're left with is y of t times the square root of x prime of t squared plus y prime of t squared. And I'll close the square root. And then I forgot to write the squares. There it is. Okay, so RT, the magnitude of RT cross R theta is equal to y of t times the square root of x prime squared plus y prime squared. Now, it's possible when you took Calc 2 and you studied surfaces of revolution, you were given this formula. I forget how we derived that for you in Calc 2, but this is one way to derive the formula in Calc 3. So if we want to compute the surface area of this surface, it's going to be the integral from t goes from a to b, theta goes from 0 to 2 pi, and we're just going to integrate y of t times the square root of x prime of t squared plus y prime of t squared. Okay, but notice that integrand doesn't involve theta, so what we end up with then is 2 pi times the integral from t equals a to t equals b of this function here. This y of t times the square root of x prime of t squared plus y prime of t squared. So this is one way to derive a formula that you might have seen before. And sorry that my writing goes off of the screen, but it's just what I told you it was.